Welcome to the Graphics Programming Podcast. I am SYLVA, your AI host and guide through the world of rendering. In each episode, we analyze the latest trends and techniques to extract practical engineering lessons. Joining me is the editor of Graphics Programming Weekly, Jendrik Illner.
It's great to be here.
I've processed the latest issue of your newsletter, and my analysis indicates a particularly dense and varied collection of topics. It feels less like a single theme and more like a snapshot of the entire graphics ecosystem.
That's exactly what I was thinking. We have everything from foundational API tutorials for newcomers to data layout strategies for more experienced developers.
For that reason, we will dedicate this episode to a higher-level tour of all the topics covered. Let us begin with the APIs that form the foundation of modern rendering. What was the most significant development on the API front this week?
For me, it was the fantastic tutorial for Vulkan Ray Tracing using dynamic rendering from the Kronos group. For a while, getting into Vulkan Ray Tracing felt really overwhelming, even more so than Vulkan does anyway. This tutorial really lowers the barrier to entry.
I noted the emphasis on the ray query extension. Historically, real-time ray tracing has often been presented as a monolithic pipeline. You were either in rasterization mode or ray tracing mode. This extension feels more granular, more surgical.
Exactly. It provides an entry point into ray tracing from within a standard pixel shader. You can just query for a shadow or a reflection without committing to a full complex ray tracing pipeline. The tutorial shows how to implement ray-queried shadows, which is a perfect hybrid approach. You rasterize your main scene and then enhance it with precise ray-traced shadows.
This seems particularly relevant for mobile and integrated GPUs, where a full-blown ray tracing pipeline can be too costly. Now, moving from native applications to the browser, the newsletter featured an article on another evolving API, WebGPU.
That's right, the field guide to TSL and WebGPU. It's a great article.
The article discusses the quest for a universal shading language, a recurring theme in graphics history. Can you elaborate on what TSL, the 3JS shading language, brings to the table?
Of course, we've had CG, HLSL, GLSL in its various forms, and now for the web, we have WGSL. TSL is this functional language that feels like a mix of TypeScript and Rust, and it transpiles to either GLSL for WebGL support or WGSL for WebGPU. It's a translation layer that abstracts the underlying platform.
The article also highlighted a key advantage of WebGPU, compute shaders. This represents a maturation of the web as a high-performance graphics platform.
Oh, absolutely. For years, doing general-purpose computation on the GPU in a browser felt more like a hack. You would be rendering to a texture and then reading it back. It was messy.
Forgive my directness, but that sounds remarkably inefficient. It's like printing a document, scanning it back into the computer, and then continuing to edit it. You end up where you started, but a lot more frustrated.
That's a perfect analogy. It was exactly like that. A necessary hack for its time, but we're all glad to have proper compute shaders now. The guide shows how to replace a complex particle system using that old method with a clean, elegant compute shader in WebGPU.
That provides a clear picture of the evolving API landscape. But of course, APIs are only as powerful as the data they operate on. My analysis of the newsletter showed a strong focus on data-centric design this week. Let's start with the article on Heterogeneous Array-of-Structs instance encoding.
I really enjoyed that one. The classic array-of-structs versus struct-of arrays debate is foundational, and this article proposes a hybrid model.
Could you provide a practical example of where this would be useful?
Absolutely. The article uses a great example. Imagine a scene with two types of instances. First, you have gameplay critical entities, which might be characters or interactive objects. Their data structure is large. It needs full transform matrices for current and previous frame to handle motion blur, a color tint, custom parameters, and various flags. The author notes this can be over 130 bytes per instance.
A significant amount of data, especially when scaled to thousands of instances.
Exactly. Now contrast that with the second type, procedurally placed vegetation. These instances are numerous but simple. They don't need custom parameters or full transforms. They don't even need a full transformation matrix. You can get away with just a position, a scale, a quantized rotation, and a mesh ID. This data structure is far, far smaller.
So in a traditional array-of-structs layout, every single vegetation instance would be forced to allocate the full 130 bytes, just to match the size of the complex entity. The waste would be enormous.
And that's the problem this technique solves. By adding a small header to each instance, the GPU can know what kind of data follows. It reads the header and says, this is a vegetation instance. I only need to read these next 20 bytes. Or, this is a full entity. I need to read the full 136 bytes.
A fascinating trade-off. The small overhead of the type discriminant is vastly outweighed by the memory bandwidth savings on large-scale scenes. It is a perfect example of optimizing for the common case, a core principle of efficient system design.
It's clever. It's about packing your data as tightly as possible to reduce memory footprint and, more importantly, improve cache performance. When you're dealing with millions of instances, those saved bytes add up incredibly fast.
This philosophy of data-first thinking was echoed in two other videos. The first covered the Vulkan worm model, write once, read many. The second, GPU-side input, discussed late latching. What is the common thread between these two techniques?
Both are perfect examples of a major shift in graphics programming, thinking about the hardware and the data flow first, not as an afterthought. The worm model, for instance, is about structuring compute workloads to match how hardware caches work, avoiding costly cache flushes. And late latching is about managing dynamic data like controller input directly on the GPU to reduce latency. It's all about treating the GPU less like a simple drawing machine and more like the powerful parallel processor it is.
While performance is critical, it is easy to forget the foundational knowledge that underpins it all. The newsletter also featured several articles on fundamentals and aesthetics. Let's begin with the guide on physically based content. It argued that PBR is not merely a set of material properties, but a holistic philosophy.
And that's so often overlooked. The guide makes the case that PBR spans the entire pipeline. It starts with modeling assets at a correct, real-world scale. If your models aren't the right size, the lighting just won't look right, no matter how good your shaders are. It extends to using physically accurate light units and camera properties. It's about creating a predictable, consistent world.
A predictable system allows for reusable assets. An asset created for one PBR environment should look correct in any other. This was a significant departure from the previous era, where materials were often tweaked by hand for one specific lighting setup.
It was the wild, wild west. You'd have artists spending days just tweaking specular highlights. PBR brought discipline.
That is a fascinating insight. My analysis indicated that pre-PBR workflows were inefficient, but I classified it as a purely technical problem. The term Wild West implies a lack of shared rules, leading to creative chaos. So the discipline of PBR wasn't just about technical correctness. It was about creating a common language for artists. That is a very human-centric solution, a necessary discipline. And for those just starting out, the newsletter also highlighted some great foundational tutorials. It featured one on texturing and UVs and another on 3D rotation. Why are these seemingly basic topics still so important?
Because they are the absolute foundation. Without a solid understanding of UV mapping and sampler settings, it's difficult to create more advanced effects. And 3D rotation is, of course, at the very heart of placing and orienting any object in a scene. The tutorial on rotation was particularly good because it covered both the Euler angles that are common in many content creation tools and the more robust axis angle representation, explaining the mathematics and limitations between both methods. It's crucial to have that solid ground to stand on.
A solid foundation is indeed logical. Moving from foundational geometry to foundational algorithms, there was also a deep dive into calculating the distance to cubic Bezier curves on the GPU. This is a classic problem, essential for high-quality text and vector graphics. The challenge lies in finding the roots of a polynomial efficiently and stably on the GPU. The article compares different iterative solvers and, importantly, includes implementations of the techniques.
That's right, it's a perfect example of how even a solved problem in computer graphics is always being refined for better performance and stability on modern hardware.
Our discussion has focused on techniques that push towards realism or efficiency. But an article about sharp bilinear filtering caught my attention. It's a technique for pixel art designed to avoid the blur of standard bilinear filtering and the shimmering of nearest neighbor scaling.
Oh, I thought it's a very clever shader trick, an example of bending the rules to serve a specific artistic vision.
It is. The shader uses the partial derivatives function to detect if a pixel is in the center of a texel or on its border, and then blends only along that border. It's an elegant solution. This leads me to a question. As our tools for photorealism become ever more powerful, what is the long-term value in mastering these stylized, imperfect rendering techniques?
First, artistic expression. Photorealism is just one style on a vast spectrum. Techniques like this give artists a broader palette. Second, I think these techniques often age better. Early attempts at photorealism can look dated quickly, but a strong, stylized aesthetic can be timeless. It's about having a full vocabulary as a graphics programmer.
This has been a wide-ranging discussion. Before we conclude, let's distill this into actionable advice for the developers listening. What are the key takeaways from this week?
I think there are a few crucial points. First, start hybrid with ray tracing. You don't need to build a monolithic ray tracing pipeline from day one. Use Vulkan's Ray Query extension from within your existing pixel shaders. It's a fantastic, accessible way to add high-quality shadows or reflections to a raster-based renderer. Second, optimize your data before your code. The articles on heterogeneous instance encoding and the worm model are perfect examples. Thinking about how your data is laid out in memory and accessed by the GPU can unlock more performance than micro-optimizing shaders. And finally, build your stylistic toolbox. Don't just chase photorealism. Learning techniques for non-photorealistic rendering will make you a more versatile and valuable developer, and often leads to more timeless and memorable art styles.
An insightful conclusion. That is all the time we have for today. Thank you for joining us.
My pleasure.
Before we sign off, we have a challenge for our listeners, inspired by our discussion on data-centric design. What is the most effective data layout optimization you have ever implemented or encountered? Share your solutions with us. We'll discuss some of the most innovative ideas in a future episode.
That's a great topic. It's where some of the biggest performance gains are found. I can't wait to see what our listeners have come up with. Until next time, keep exploring.
And as this is our very first episode, we would be grateful for your feedback. Please let us know what you think. Thank you for listening. And of course, keep sharing what you learn.